Okay, hi everyone. Welcome to another Graphs and Matroids seminar. Today we have Natalie Behague from Ryerson University, although she's going to be at UVic soon, I believe. And she's going to be talking about subgraphs in semi-random graphs. Go ahead, Natalie.
Thank you, and thank you very much for inviting me to talk. It's a pleasure. So yeah, I'm going to be talking about subgraphs and semi-random graphs. This is all joint work with Trent Marbach, Paul Prala, and Andrei Ryshinsky. So let's start by defining a semi-random graph. So this can be thought of as a one-player game. And how it works is you start with n vertices, and on the tth time step, a random process, uniformly at random, selects a vertex, ut, and the player of this one-player game gets to pick a vertex vt, and they add the edge ut vt. So I'm going to attempt to draw on. So suppose the random process gives you this vertex. You as the player, maybe you choose to add this edge. And then the random process gives you this vertex. You as the player might choose to add this edge. And then so on and so forth. You can add whatever edge you like at each time step, so long as it's connected to the random vertex that you're presented with. And we call the graph after t steps ht. So the questions that we're interested in for these semi-random graphs are, what properties can the player force the graph to have, and how long does it take to get that property? And we're going to talk about this in the context of thresholds. It's all random. So if P is a graph property, we're going to ask that P is monotonic. So that just means that if a graph has the property, adding more edges to the graph keeps that property. And the reason we ask for that is so that once you've made the property, further time steps, the property just carries on. So then it makes sense to ask the question, at what time t does this property occur? Well, obviously that depends on the player's strategy. So we're going to be asking for some kind of threshold, which will be a function of n, the number of vertices, such that for any player strategy, if the time is a lot less than the threshold, then asymptotically almost surely the property does not occur. And if and also in the other direction, if the time is a lot bigger than the threshold, tau, there exists a player strategy such that asymptotically almost surely they can force the property to happen. So you have these two directions. You're saying if your time is a lot less than the threshold, no matter what they do, they just can't force the property. If the time is a lot greater than the threshold, they can do something to force the property. And asymptotically almost surely just means we're only looking at this as n tends to infinity. I'm being purposefully vague about what much less than and much greater than means, because it will depend on the context and what the property is. So I'll give some examples. So suppose the property we were looking at is no isolated vertices. So the player is trying to force the graph to have no isolated vertices. So if we have some trivial bounds, if you have fewer than n over 2 edges, so if the time is fewer than n over 2 steps, you definitely will have some isolated vertices. You just can't cover them all. So that's the trivial lower bound on the threshold. Also, the player, if they wanted to, could just label all the vertices 1 up to n, and independently of what the random process presents to them, they could always just join on the tth step, join and the edge to the tth vertex. So in that way, they have some algorithm that gives a threshold of n, at the most n, just by on the tth time step choosing vt to be the tth vertex. But they can do better than this. So if you think about this a little while, an obvious strategy seems to appear. What are you going to do? Well, you have some set of, at time t, you have some set of vertices that haven't been used yet. So all you're going to do is the random process is going to give you a vertex, and you're going to pick one of the currently isolated vertices and join an edge to that one. Okay. So if you work through the details, I don't want to go into in great detail, but if x sees number of isolated vertices at time t, the probability that the random process chooses one of those isolated vertices is this at time t minus 1. And then with probability 1, you pick the player picks a vertex that was isolated. So this is what we expect the number of isolated vertices at time t to be in terms of the number of isolated vertices at time t minus 1. And so you can get some recursion going and basically work out that the threshold is log 2 of n. So the player's strategy is always to pick a new isolated vertex to join to. It's also clear that that is optimal. You can't improve on that if you think about it a little while. So we get this log 2 ln. And it's interesting to compare this to the random graph. So if you take the Elish-Renyi random graph with the same number of edges, then to get no isolated vertices, you need the number of edges to be like n log n over 2. So this is behaving very differently to that. And you probably expect that, right? Because it's only semi-random. The player has some kind of power over what they're doing. Okay, so let's think about some other global properties. So we had no isolated vertices, the threshold is log 2n. An easy one to consider is if the property is being connected. So to be connected, you need at least n minus 1 edges if you have n vertices. And in fact, you can always force the graph to be connected after n minus 1 moves if the player just always picks the same vertex to join an edge to. Then you end up with something like if the player always sort of extends it like a tree, then they can basically keep on making it like a tree, and every time they're given a new vertex, they can join it to the connected component they have so far. So again, the details I will leave to you, but the threshold is like n. Okay, so something a bit more complicated, just to show you that it's not always so straightforward to get an exact threshold. What if the property is having a perfect matching? Well, this was studied by Gowan, McCurry, and Pratt, and they found this lower bound of 0.955n on the threshold and an upper bound of 1.209n. They also studied, with Kaminsky, they studied having a Hamilton cycle, and they found these even further spaced apart bounds. 1.219n is the lower bound and 2.611n is the upper bound. So it's quite difficult to get a handle on exactly what's going on here. And I should say that in this context, what I mean by much less than or much greater than the threshold is that if you have some smaller constant times n, then no matter what your strategy is, in that number of time steps, you can't make the thing. And if you have some larger constant than this times n, then there exists a strategy that's that you can make the property happen. So in this context, when we're talking about thresholds, we're talking about working out the constant that has to go in front of n. Okay, so those are all global properties, and it's clear that these global properties, well, they're all stronger than having no isolated vertices. They're all going to take a linear number of moves in n. What if instead we look at something that's more of a local property, rather than asking the entire graph to have something? What if instead we ask for the most general local property? We fix some subgraph G, and the player wants to make this subgraph occur. So let's start with an example, just so you know what I'm talking about. So suppose the graph we fix a subgraph to be a path on 3 edges. So the player is attempting to make a path on 3 edges. Well, what do they do? Well, suppose that the random process gives them this. They can join it anywhere. And maybe the random process presents them with this. They can do this. Remember, they're trying to create a path. So they're thinking about making a path. The random process gives them this maybe next. They join it to the end of their path so far created. And in fact, so long as the random process is giving them a new vertex, they just join it to the end of the path they have so far and they can extend their path. So this takes 3 moves. It asymptotically almost surely takes 3 moves because you need the random process to give you a new vertex that you haven't seen already. But as n tends to infinity, the probability that the random process gives you a new vertex in each of your 3 time steps is very high. So asymptotically almost surely they use this strategy to do it in 3 moves, and obviously they can't do it in fewer than 3 moves because they need 3 edges. So that's a path. Let's do another example. Let's do a little star on 3 edges. Okay, so suppose they get the same random vertices. So the random process gives them this. Maybe they join it here again. Random process gives them this. Maybe they think, oh, well, I'll just join it to the same one. Random process gives them this. They join it to the same one. Oh, look, they've done it. So this one, again, if the random process gives them a new vertex, they just join it to the special vertex they've chosen, and they can make their star so long as they get a new vertex every time. So this asymptotically almost surely also takes 3 moves. And actually, there's nothing special about the path and the star here except that they are trees. So the key thing was that every time the random process presented them with a new vertex, they could add an appropriate edge to what they'd created so far to extend towards a copy of G. And clearly, if G is a tree, that kind of process is going to work. So you just order your vertices such that every new vertex, when it was added, is a leaf. And then to add in the edges one by one, you just use this whenever the random process gives you a vertex that hasn't been seen so far, you add it in the appropriate way to extend your tree to the new leaf. So if we have a tree on C edges, then asymptotically almost surely we just take C moves and the threshold is C. Okay. So trees seem to be done. Trees seem to be very easy to do. So what's the next thing you think of that's not a tree? Maybe it's a cycle. So let's think about trying to make a cycle. So again, let's have a play. Maybe the random process gives us this. Random process gives us something new. And we try and put in some edges. It's not entirely clear what we should do. If you play around with this for a while, you'll realize that if the random process only presents you with new vertices that aren't currently that don't currently have an edge connecting them, then you can never close off a cycle, because all you're going to be doing is creating a tree or a forest. So if you never see a vertex that has already got an edge connected to it, you can only make forests. So we need that at some point the random process gives us a vertex we've already seen in order to make this a cycle. Okay, so what do we need to be presented with an already used vertex? There's this little calculation here. So at time step I, what's the probability that the random process picks a vertex that was already seen? Oh, there's a mistake here. This should be a 2 here. What's the probability the random process presents with a vertex we've already seen? Well, it's 2i over n, because there are at most 2i vertices that have an edge from them. So at time I, there are at most 2i vertices that have an edge from them. The probability that the random process picks one of them is 2i over n. So if we sum that up over all time steps from 1 to t, then we see that the probability that at some point in the first t time steps we were presented with a vertex we already saw is like t squared over n. The expected number of times that happens is like t squared over n. And we need that to be greater than 0 if we have any hope of making our cycle. So in particular, if t is like root n over omega for any function omega that tends to infinity with n, then we know that there's no hope of making one of these cycles. Asymptotically, almost surely we can't make one. Okay, on the other hand, suppose that we have a t that is greater than root n. Well, we can just use this following strategy. So we make a path like this. Every time the random process gives us a new vertex, we just extend the path. The first time the random process picks a vertex that we've already seen, perhaps it picks this one, then we can close off our cycle, because so long as our path had more than 3 edges, we can close off our cycle. So what that tells us is that using this strategy, all we need is that the random process picks the vertex we already chose. So this tells us that we can, if t is greater than root n, if t is root n times omega for some function omega that tends to infinity, by following this process, we can create a cycle. So in particular, the threshold is root n. So notice that in this context, compared to the global context, I'm allowing myself a little bit more wiggle room with what a threshold means. So in these contexts, I'm going to be caring about the power of n and not the constant in front of n. And I'm going to say that something is a threshold if there's some function omega, if any function omega that tends to infinity with n, if t is like the threshold over omega, asymptotically almost surely we can't make the thing. And if t is like the threshold times omega, there is some strategy to make the property. Just if you get confused with what I just said, it's exactly the same as what I've done on this, but for general thresholds. So, okay, we had that for trees, the threshold was like a constant. And we have that for cycles. Obviously, this generalizes to all cycles. This wasn't special for 4 cycles. We get that the threshold is like root n. So the next question is, what is, for general subgraph G, what is driving this power of n on these thresholds? Okay, well, if you're like me or like some other authors, we'll talk about in a minute, you might guess that perhaps it's the minimum degree that's driving these. So why might you think it's the minimum degree? Is because cycles have leaves, and trees all have leaves, and it was the leaves that was crucial in being able to build up the cycles. It was the leaves that was crucial in being able to build up the trees in a constant number of steps. Cycles don't have leaves. They have these all their vertices have degree 2, and it was somehow a problem with the degree 2 vertices that forced us to have root n. So minimum degree might be your first guess, and I've given the game away. Minimum degree is not the answer, for the simple reason that if you want to make this, and if you want to make this, it must be at least as hard as making this, right? So this has minimum degree 1, but it must have a threshold at least as bad as root n, because it's at least as hard to make as this. Okay. So rather than minimum degree, we're going to want something like the maximum minimum degree over all subgraphs, which has a name. That's just the degeneracy. So let's do a little detail and talk about degeneracy. So what I just said, the degeneracy D is the minimum D such that every subgraph has minimum degree at most D. So in particular, it's the maximum minimum degree over all subgraphs of your graph. Another way of defining degeneracy, which may be more familiar, is there's an order on the vertices. It's the minimum D such that there's an order on the vertices where each vertex has at most D edges to earlier vertices. So I've called that left degree. It's like degree to earlier vertices. And one more definition on degeneracy before I move on. The D core is the maximal, as the subgraph that exhibits the degeneracy, is the maximal subgraph that has minimum degree D. So we know that there must be some subgraph with minimum degree D by the definition, and the D core is just the maximal one. So it's just something that gives you that minimum degree D. Okay, just a little recap on degeneracy, and hopefully that was fairly familiar. So I claim that degeneracy is going to be the thing that's driving this subgraph property. So let's talk about some previous results, because other people have thought about this before us. In particular, these authors, Ben Eliezer, Heifetz, Cronenberg, Parchik, Schickelman, and Stojakovic in 2020 proved an upper bound on the threshold in terms of the degeneracy. So they've shown here that if you have a graph of degeneracy D and you have some function that tends to infinity with n, then if you allow yourself to have n to the 1 minus 1 over D times omega rounds, then there exists a strategy such that you can asymptotically almost surely make a copy of G. So this is like an upper bound on the threshold. I'll give you a quick sketch of how their proof goes. So what you're going to do is you're going to use the degeneracy order. So you're going to order the vertices such that each vertex has only D earlier neighbors, and you're going to try and build G one vertex at a time. So all you need to do to do that, so you suppose you have K vertices, you split your time, your n to the 1 minus 1 of E times omega total number of time into blocks of size, into K blocks. So each of those are still going to have, n to the 1 minus 1 over D times omega bits in it. So all you need is that in each of those blocks, there was some vertex that was chosen D times. So if that's the case, then in the first block, we just put in the first vertex. In the second block, we create a copy of the second vertex and so on. So in the ith block, we're going to try and add the ith vertex to our copy of G so far. And how we're going to do that is every time the random process picks a vertex, we treat that as if it was the ith vertex and we add an edge to our current copy of G. And when we have added, if the random process picks that vertex a second time, we add a second edge to appropriately. And so in this way, if the random process, when it eventually picks some vertex D times, we'll have all the D edges we need from that vertex. And so we'll have created the ith vertex in our copy of G, and then we can move on to making the I plus 1th vertex. So as long as within each block there is some vertex that was chosen D times by the random process, we can build our copy of G in this degeneracy order way. And it turns out that this value, this n to the 1 minus 1 over D times omega, is just the number of steps you need to ensure that the some vertex is randomly chosen D times. So how can you see this? Well, the number of vertices chosen once is like T. The number of vertices chosen twice, we already saw that. It's like the sum from I equals 1 to T of I over n, which goes like T squared over n. You can see the number of vertices chosen 3 times is going to be like, well, on the ith time step, the probability we choose a vertex we chose twice will be like I squared over n. So it's going to be I squared over n squared. You sum that over all time steps. This is how you get this T code over n squared. So in general, the number of vertices that are chosen D times will be like T to the D over n to the D minus 1. And so if T is like this, then asymptotically, almost surely there are some vertex that was chosen D times, which is exactly what we needed. That was a probably raced through a little bit, but that was a quick sketch of the basis of that proof. They weren't able to prove a general lower bound, but they were able to prove a lower bound on the threshold for complete graphs. So I'll mention that. So if G is a complete graph, its degeneracy is, if G is KK, its degeneracy is K minus 1. And they showed that if you only allow yourself n to the 1 minus 1 over K minus 1 over omega rounds, no matter what strategy you use, you cannot make a KK asymptotically almost surely. Again, a quick sketch of the proof. The way that this proof works is they use induction on K, and they show that the expected number of Ks at the Tth time step is like T to the K minus 1 over n to the K minus 2. So here's how this works. So here's going from triangles to K4. So the expected number of triangles is T squared over n. And then to make a K4, the random process needs to pick a vertex of one of those triangles. So it needs to pick this vertex. And then the player can create a K4 potentially. They can create at most one K4 for each triangle the vertex landed on, because they only make one edge. And so there's only one K4 per triangle. So that's how they sort of bounded the number of expected K4s based on the number of triangles. It's that the random process needs to land on a triangle, and then for each triangle it landed on, you get one K4. So you're sort of doing this sum to go from the K minus 1 to the K, you're doing this sum. Okay, So those are their previous results, and what we have managed to do, me and my co-authors, Trent Marbach, Paul Polat, and Andrei Roginski, is do the general lower bound. So we've shown that for any graph of degeneracy D and some functional omega that tends to infinity, no matter what your strategy is, after n to the 1 minus 1 over D over omega rounds, you can't create a copy of G. And before I outline the proof, I just want to say some reasons that this was not immediately obvious to the previous authors, and some reasons why this is a bit more difficult than their theorems. So the first difficulty is we can't use, my pen's not working. That's very annoying. There we go. Right, so if we will try to use their first proof, their first proof was saying, so to get a lower bound equivalent, you might want to say something like some vertex has to be chosen D times, and we had this bound on the expected number of vertices, we had this expected number of vertices that were chosen D times, and so you say if some vertex is forced to be chosen D times, then we have this lower bound as well. The problem is, it's not true that some vertex is forced to be chosen D times by the random process. So here are some examples. This 4 cycle, it has degeneracy 2, but suppose that we say, well, maybe it was constructed where the random process, my pen's still not working. Maybe it was constructed where the random process, so I've drawn these directed arrows, and you should think of them as the out bit is where the random process landed, and the in bit is where the player chose the vertex. So the random vertex was the one that is going out of. So suppose that the cycle looked like this as it was being constructed. The random process here never chooses a vertex more than once. So it does choose a vertex that the player has chosen, but the random process itself never has to choose the same vertex twice. So there's something a little bit more complicated than just the random process picks the same vertex twice. And there's a more complicated example here, which is the K5 that has degeneracy 4, but the way I've drawn it, it only has out degree 2. So again, if it was constructed in this way within our semi-random graph, the random process would only have to choose the same vertex twice, but the degeneracy is 4. So you must somehow have to take into account the player's choices on and the fact that the random process might have to pick a player-chosen vertex, not just a previously chosen random vertex. So that's one issue with trying to use the first proof. And the other first instinct you have is try and extend the complete graph proof. So I mentioned that there's this proof that on lower bounds for the complete graph, so why can't we just easily generalize that? Well, the problem is if there's something like this. So what's special about this graph is if you remove this top edge, then you have something with degeneracy 2 that's disconnected. And when you put in this top edge, it becomes something of degeneracy 3. And the reason that this disconnectedness is unhelpful for us, differently to the complete graph case, is, well, what I said in the complete graph case, you make at most 1 K4 every time the random process lands on a particular triangle. You make at most 1 K4 associated to that triangle, so you get this handle on the expectations of the numbers of K4s. If you try and do something similar for this kind of world, where you just say, I have the expected number of each particular kind of subgraph, and then I try and get an expected number of copies of the whole graph, we run into a problem here because maybe I created lots of copies of this, so the random process picked this vertex here, but maybe I could simultaneously create lots and lots of copies as the player of this graph if, say, I connected it to some vertex like this, where there are loads of these little houses attached. So rather than it being sort of one-to-one, I've now potentially made loads of things at once. And it seems like it's hard to do that because maybe there aren't very many of that kind of vertex, but you only need one of that kind of vertex because you as the player get to choose it. So you won't be worried a bit about about this kind of situation, and that breaks any kind of simple expectation argument that just uses the whole graph in its totality. So you have to do something a little bit more nuanced. Okay, so I'll give an outline of the proof. So the first thing we do is we just focus on the decor, because if we focus on the decor, we just care about minimum degree. We don't need to worry about degeneracy. So if you can show that this lower bound holds for graphs of minimum degree D, then you win. The second thing we're going to do is, given our fixed graph G, we're going to fix some orientations of the edges, and we're going to fix an ordering of the edges. So here's an example. We fixed some orientations of the edges, and we've also numbered the edges in this order: 1, 2, 3, 4. And what we're going to do is we're going to show that for a specific order of the edges, that they must appear as we construct it within our semi-random graph, and also insisting that as we construct it, the random vertex is always the vertex that's the out end of the edge, and the Plato-chosen vertex is always the vertex that's the in end of the edge. So in order to create this, I'm insisting that I first create this edge, and then I secondly create this edge, and then I thirdly create this edge, and I fourthly create this edge. So I'm going to specify a particular order that I had to make this in. Let's get rid of that. The reason we do this is actually, it seems like I'm adding an extra layer of complication, but it's actually a lot easier to get a handle on what's happening if you fix a particular way that your graph is constructed. And then the end of the proof, you say, okay, well, for any orientation and any edge ordering, asymptotically, almost surely we couldn't construct that specific one. There were only finitely many ways of ordering the edges and fixing orientations. So if we can't construct any single one of them, we lose. We couldn't have constructed the graph G. Okay, and then the third bit is the clever bit. What we're going to do is we're going to define a weighting on the vertices of G that will depend on this orientation and edge ordering that we specified. We want our weighting to have two properties. The first property is that the weighting captures the number of vertices in the semi-random graph that can be the image of that particular vertex of G. So suppose in our graph G here, this vertex had weight 2. That would be trying to capture something about how many copies of that particular vertex sitting within a copy of G with this particular orientation and edge ordering within our semi-random graph. So in particular, we're going to want that the number of vertices in our semi-random graph that look like the image of V within a copy of G is like T to the weight over n to the weight minus 1. And the other property we want our weighting to satisfy is that all the vertices have weight at least a minimum degree. So that's because we want it to satisfy this this thing that I said in the first bullet point, which is that if our minimum degree is D, then we want that it's we're aiming for a lower bound that depends on the minimum degree. Okay, so if we had those two properties from a weighting, we would win, because then immediately it says that, I mean, just pick one vertex, says that the number of vertices in HT that are the image of that vertex is like T to the delta over n to the delta minus 1 at most. And so if T is small, if T is less than, T is like 1 minus 1 over delta over omega for some function omega that tends to infinity, then we just don't have enough vertices. There aren't any vertices that look like the image of V, asymptotically almost surely. So if there are any vertices that look like the image of particular vertex of G, then clearly there just aren't any copies of G within our graph. Okay, so if we could find a weighting that satisfied these two properties, we would be happy. And that's what we're going to do. So how does the vertex work? How is it constructed? Well, what we're going to do is we're going to start with no edges, and we're going to add in the edges one by one in the order that we specified when we gave an edge ordering, and update the weightings on the vertices as we go along. So we start with no edges, and every vertex has weight 0. So when we add an edge, we add the ith edge that is an edge from x to y, how do the weights update? Well, the weight on x itself is going to increase by 1, and that's capturing that the random process has to land on x within our semi-random graph to make a copy of this edge. And the more unusual part of this is if a vertex v has a directed path from x to v, so if there's any directed path from x to v, then v either has its weight the same if its weight is bigger than the weight of x, or it inherits the weight from x. So what this is saying is along directed paths, weights are inherited. But if your weight was already bigger, you just keep your bigger weight. So your weight, the weight of a vertex never decreases, but sometimes it increases if it's on a directed path from some vertex x that was where the random vertex must have landed. Okay, so that was probably what to take in. So let's just do an example with my graph that I had on the previous slide. So at the start, every vertex has weight 0. Then we add in our first edge, and the weight on x increases by 1, and also the weight on y, which is the other end of the edge, increases by 1 because there's a directed path linking x and y. So these both get weight 1. Then we add in our second edge, which is this one. So this is the out vertex, and that gets weight 1. And then anything that's on a directed path from that will inherit the weight, but they already had weight 1, so they don't change. Now we add in the third edge. So this vertex is going to update from 0 to 1. And then anything that's on a directed path from that will update its weight, but it's only this vertex. And finally, we add in a fourth edge. So this vertex increases from 1 to 2, and anything that's on a directed path from that vertex, which is all of these three, will also increase their weights to 2. But this one remains at 1 because it's not on a directed path from this. So it seems like a very simple weighting. I want to stress at this point that the weighting is actually the clever idea. So once you have the correct definition of a weighting, the correct way of capturing how difficult each vertex is to put into your semi-random graph in this way, the rest of the proof is fairly straightforward. There's some difficulties, some technicalities, but this is the real idea, is correctly capturing what becomes difficult to put into your semi-random graph. So these weights are attempting to capture how hard that vertex is to put in the semi-random graph. It's like, how many times must the random vertex pick something that was already chosen to make that particular vertex happen? So maybe unsurprisingly, this thing is easier to make than these things, because this thing is kind of like a leaf that you just stick on. So you just need the random vertex. You just need a random vertex to land on anything, and you can put in this edge. Whereas these things that are in a cycle are unexpectedly have weight 2 because it's capturing that the random vertex has to pick something. The random process has to pick something that was already picked to make a cycle. Okay, so let me give a little bit more detail on the meat of the rest of the proof, but remember that this is like the key idea. Okay, so we need to prove that this weighting works. There are 2 parts to proving that the weighting works. The first part is that the random graph actually does inherit the number of copies of each vertex that's sitting in the random graph is like t to the weight over n to the weight minus 1. So how do we prove that? Well, we have this function that is the thing I said it's going to be. It's going to be the number of vertices in our random graph that are a copy of v within a copy of gi. So there's all these parameters. Gi is like the graph G with the first I edges in it. So G0 has no edges and G1 has the first edge, and so on. And we're going to try and prove that the expected number of such vertices is like t to the weight at the time, the wi, which is like the weight of the vertex in gi over n to the wi of v minus 1. And this is multiplied by some constant. I don't think you should worry about the constant. The constant is there because it's like an artifact of the proof. You need it to make the induction go through. But you should just think of this as like a constant. And we proved this by induction on I. So we're going to imagine we start with a graph with no edges and we gradually add in the edges and see what happens. So I won't go through all the details, as I say, but what you should think is, I'm missing some bits on this. It's weird. What you should think is that, so when you add in the edge, this next edge, so we're going from gi minus 1 to gi, we're adding in this edge xy. I don't know why this has disappeared, but that should be like that. So if we have some vertex and its weight hasn't changed, then obviously the inductive step is easy. Its weight hasn't changed, and the number of copies of it has at most decreased. So the number of copies of it that sit within a gi is harder than sitting within a gi minus 1. So if its weight hasn't changed, then we basically get the induction step for free. If the vertex was x, so if v in this equation was x, then what this is saying is that the weight increases by 1, which is like saying the random process had to land on that vertex in order to make the copy of x that sits within a gi compared to sitting within a gi minus 1. So that's also fairly straightforward. And then the difficult part, which isn't that difficult, but it's a little bit more technical, is the third kind of vertex, which is these vertices where their weight, they're on a directed path from x, so their weight is changing, but it's not that the random process has directly landed on one of them, it's that it's landed on x. And the way that this is proved, the inductive step is you have to sort of count as you go away from x, how many vertices there could be that look like the image of each neighbor of x, and then each neighbor of those, and then each neighbor of those. And this is where this annoying constant comes from, is a sort of accounting for the fact that you might get neighbors of neighbors of neighbors, but you're never going to sort of fundamentally change the number of things that could be neighbors of x. So I'm being very hand-wavy because I don't really want to go into all the gory details, but essentially the idea is you just do an induction where you add in each edge of the graph G and you check that the number of copies within the semi-random graph is informed by the weight in exactly the way we expected. Okay. The second part of proving that the weighting works is we had to show that all the vertices have weight at least the minimum degree. This is a much nicer proof, I think, less technical. So how does this proof work? Well, first of all, we're going to allow loops and multi-edges, just because it makes the argument go through more easily. So now we're allowing our graph G to have loops and multi-edges. We define all the weights and everything exactly the same way, so there's no problem there. So remember that the weight itself wasn't defined with any reference to the semi-random process, it was just defined on the graph with a given order of edges and orientations of those edges. So, okay, so what do? We do an induction, again, this time we're inducting on the number of edges of G. So I don't know why this time, we did that last time as well. So suppose that it was true for n-1 that all the vertices had weight at least the minimum degree. Then what happens at the next time step? So suppose this was our graph at time n with n-1 edges, and then we added in this edge and updated the weights. Well, anything that was on our directed path from x is good, is already fine, because its weight has increased by 1, so it's going to have weight more than the minimum degree. We might worry about these vertices over here that are not on a directed path from x. So this is our x. These vertices over here that are not on a directed path from x, we might worry about them because their weights haven't changed. So they maybe could have weight that was less than the minimum degree, but it turns out they don't, because we construct this auxiliary graph T prime, where we sort of fold in any edges that come out from this bit, which is vertices that aren't on a directed path from X. We fold them sort of onto themselves. We just create lots and lots of loops. Now, any edge that was out of one of these would just turn into a loop. This has the same minimum degree, or at least as big, could be bigger, as our overall graph, because we haven't changed any degrees. And so, and this also has fewer edges than our overall graph, because it doesn't include this edge. And so we win. We know that. And then we also have to check that the weights, as we add edges to this, actually end up with the same as this. And it's just a little check, and it all turns out to be nice. And so the fact that it works for this means that it works for this, and so it works for the whole graph. So yeah, again, that's just a little check. It's sort of saying the weight behaves the way we want it to as we add in the edges to our graph. Okay, so I have about 10 minutes left. And in my remaining 10 minutes, I want to talk a little bit about hypergraphs. So I've talked this whole time about graphs, but we can also define the semi-Riemann process for hypergraphs. So just to introduce you, an S-uniform hypergraph is a hypergraph where all your edges are sets of size S. So your hyperedges contain S vertices. And we can define the semi-Riemann process really similarly. So in general, to define a semi-random hypergraph, we're going to fix some R less than S, which is going to be the number of randomly chosen vertices each time step. We have n vertices, and in the teeth round, we have some set now of vertices, UT, which are the randomly chosen vertices, randomly chosen uniformly at random, and the player can pick S minus R vertices, which are going to be the rest of the vertices of our hyperedge, and then they add this edge that's the union of the randomly chosen vertices and the vertices that they chose. So it's just the generalization of our graph case, and we now have much more freedom because we have potentially edges of size more than 2. So the nice thing about the hypergraph case, and the reason I want to mention it, is that if R equals 1, so what does that mean? That means that the random process is choosing one vertex at each time step, and the player gets to choose S minus 1 vertices and add a hyperedge of size S. Then the behavior, the threshold for creating a subgraph, a fixed subhypergraph, it behaves exactly the same way as for graphs. So you define degeneracy in exactly the same way as the maximum minimum degree overall subhypergraphs, and it turns out that the threshold for containing a particular subhypergraph is exactly the same as for graphs, and all our proof techniques basically go through. So everything I just sketched for you, you do exactly the same in the hypergraph world in this R equals 1 case, and just be a little bit more careful with your definitions, but it's the same proof. So that's very nice. And obvious question, okay, but what if R is not 1? So this is an open problem that I want to finish with. What if we have a semi-random hypergraph where the random process picks 2 or more vertices each time step? So maybe it picks 3 random vertices each time step and the player gets to pick 2. When you want to look at creating a particular fixed subhypergraph, what is the threshold for that? Well, we have this lower bound. So the threshold for creating the subhypergraph G is at least n to the R minus K minus S plus R divided by the number of edges of G, where K is the number of vertices of G. So it's some complicated function. We can, through a matching upper bound for certain kinds of hypergraph, they're all quite sparse. So an example of something where we can prove a matching upper bound is a star. So that's something where you have one vertex that's like the center, and then all hyperedges that contain that vertex. And then in our world, so we have a star, and we're allowed to add some small number of extra edges to our star, and we can match this lower bound. In fact, we can increase the center of the star to be up to R vertices, and we can still match this lower bound if we don't add too many extra edges. But this lower bound is not tight in general. Our smallest example of something that doesn't match the lower bound is this hypergraph. So G is this thing, which is like a sort of cycle, a loose cycle on 8 vertices. So it has these 4 hyperedges of size 4 and 8 vertices. And if you try and construct this with R equals 2, then you get a different, in this particular case, we can examine it and find out the threshold, and it turns out to be different to this lower bound. So we don't believe that this lower bound is the correct one, but we know it's not the correct one in general. So that's the big open question, is what is the correct lower bound or upper bound? Can we improve on this lower bound in general? Can we improve this upper bound? Can we give an upper bound that's not trivial? And you know, what power of n do we need in these cases? And in the if you remember right back at the start of the talk, I said for the graph case that the original authors of the upper bound also managed to prove things for complete graphs. So we tried looking at complete graphs here, and so complete hypergraphs don't really seem to be any easier than the general case. So even for complete hypergraphs, we don't know what the correct threshold is. So even if you could answer the question, what is the threshold to have a sub-hypergraph that's a complete hypergraph? We know for some really small cases, but we don't even know for, say, 6 vertices and edges of size 3. So that in itself would be a good start. Thank you very much.
Thank you so much, Natalie. Let's do a round of applause if everyone can unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3. All right, and does anyone have any questions for Natalie? If you do, you can unmute and ask.
Are there any conjectures about the threshold for finding a fixed graph as a minor of a semi-random graph?
That's a very good question. No, not as far as I know. So this construction of the semi-random graphs is fairly new, and so all the papers I referenced, the ones that found these global properties are all from 2019, 2020. So I don't think anyone's really thought about something like minors. No, that would be an interesting thing to look at.
What's the threshold for being too connected?
I don't know. Yeah, I don't know.
So it's got to be some function of n, I guess.
Yes.
And you've got the threshold for getting a Hamilton cycle, so that guarantees too connected. So it's going to be something less than the Hamilton.
Less than that.
Yeah. I'm surprised that hasn't been looked at.
No.
Okay.
I don't think so.
Thanks. Nice talk.
Thank you.
Any other questions? That's all I see for now. So I'll end the recording there and then we can have some informal discussion. Thanks again, Natalie.